Let's look at some of the specific timing constraints. In this module, we'll be looking at clock constraints and how to set clock latency, uncertainty, things like that, and also any other kinds of clocks like generated clocks, gated clocks, virtual clocks, so on and so forth, and also how to set constraints like input delay, output delay constraints, which are relative to the clock. In this module, we'll identify the constraints on the different types of design objects after identifying what design objects are, and then look at design level constraints, environmental constraints, and all the different types of constraints that there are in your SDCs. Operating conditions are something that you would apply at the design level. So nowadays, we have specific library files created for a specific set of operating conditions. So you can specify just the library and that itself is sufficient. But if you are reading in multiple libraries and you want to use a specific set of operating conditions, then you would use the set operating conditions command and set that particular operating condition that you want to use as your default operating condition for timing analysis and so on and so forth. So as the design process varies, you might actually have to change this operating condition often to get different timing data. Now, for the situation where there is multi-mode, multi-corner designs, where you have a particular design being verified for different modes and different corners. A corner is one specific set of process, voltage, and temperature. So if you are verifying your timing across multiple corners, then you would have to specify your operating conditions according to the corner that you're actually verifying currently. The design rule constraints are applied at the design level. These design rule constraints must be met so that your design can be manufactured. And these rules actually come from the fabrication process, and so therefore you must set these design rule constraints according to the fabrication process. The environmental constraints are typically applied at the port level. So the environment of the chip obviously has an influence on your chip performance, and you need to model the environment in terms of the constraints. So basically a driving cell is something that drives the input of the chip, and the load is what must be driven by the output pins. So both of these must be accounted for when you're actually designing your chip, and so therefore how much load can it drive, and what is the driving cell that is driving your input pins. Both must actually be specified for your design to work properly. If you know what specific cell is driving the input of a particular pin, then you can actually set that using the set driving cell command. And by defining the driving cell, you're basically defining what the strength of the incoming signal is, or its capacity to drive the input and the fan out of that particular input pin. So you can actually use the set driving cell command to tell the SDA tool or whatever tool it is to use this particular SDC constraint to determine the driving cell of that particular input pin. You can define what the load of an output port is, which is the total amount of capacitance that the port has to drive by using the set load command. Or you can also specify the set fan out load and set port fan out number, a combination of these two, to determine the load. So per fan out what the load is and how much fan out it is, both of those in combination can determine your total load that this particular output pin actually sees. So basically look at the notes to see examples of port fan-out number and fan-out load values and examples. Wire load models are applied during synthesis to determine the wire delays, and these wire load models are characterized based on area. So when there is no wire load model specified, the tool automatically selects the default from the library, and if you want to specify the model for a block, you can actually specify the set wire load model command. So normally you have a wire load mode and wire load model, and both of these in combination would actually determine what wire load model to use for a particular net. So, but when nothing is specified, it goes based on what the defaults are from the library. So the wire load modes are what determines how the net delay calculation actually happens. In the case of the top mode, all the net delays in the entire design actually use the top model, and in the case where you have a wire load model that is considered as large, now that large, if it encompasses the entire area of the design, then that is basically what it would use, what the SDA tool would actually use to calculate the net delays. So basically this is very pessimistic, and so you can actually use this to make sure that your design is extremely conservative. Now the other end of it all is using a zero wire load model. So in the case where you just want to see if the design would actually meet timing even without any wire delays, then you could use the zero wire load model option. Now, if you want to force a particular subdesign to use a different wire load model than the one from the top, you can actually specify the set wire load model uh, command for that particular design or subdesign. The other wire load mode is the enclosed mode. So let's say for the purposes of an example, if your entire design is actually 8,000 units, and the average one is 4,000 units. So the block B would actually be encompassed in under 4,000 units, whereas the entire design would actually take 8,000 units. Then in which case, uh, if you set the enclosed mode, block B would actually choose the 4,000 units because it can be enclosed in the 4,000 unit model. But for the rest of the design nets, the tool will actually use uh, the um, the large, which is the 8,000 unit wire load model. Now, extending the same logic, if there are blocks A and C, and they would fall under the category of small WLM, let's say 1,000 units, then basically you would actually have all the nets under block A and block B use the small WLM, which falls under the 1,000 units. So going by that example, if we look at the multiple nets in this design, net 1 basically uses whatever encompasses that particular net 1, which is block B, and therefore uses average WLM. Net 2, the entire design is actually encompassing it, and block B nor block C can contain that particular net 2, so therefore net 2 uses large WLM. And net 3, because it is enclosed in block C, will use the small WLM. In the segmented wire load mode, what the tool does is basically it breaks down the entire design nets into small chunks, and depending on what encloses that particular chunk of the net, that model is what is actually used for that particular piece of the net. So if you look at the bottom right, the segmented mode actually shows to the different segments of the net, and what wire load models are actually used. So in the case of net 3, all of the net 3 is encompassed in block C, and therefore it uses small WLM. But if we break down the net 2, block A net 2 would use small WLM, block A B net 2 uses average WLM, and the design net 2 uses the large WLM, and block C net 2 uses the small WLM. So you're breaking down the nets into smaller pieces. This actually is, it sounds like the most logical choice, but because the tool varies in how it does the optimization, the computation is intensive and it runs very slowly, but also if there are nets that fall under critical paths, then the wire load model actually often changes because of the block that encompasses that particular net, and therefore the models and the delays that the tool generates for these nets become unreliable. So wire load models in general are not unreliable, but segmented in general, segmented very specifically, is not a recommended model for net delays. The create clock command creates a clock object with an ideal signal, and it specifies the period and the waveform, and also the ports or pins that are connected to the clock source. So if you need a duty cycle, this duty cycle is actually derived from the period and the waveform, which is the edges itself. Now, in the first example shown above, the command actually defines a clock, which is an ideal clock, and that it is connected to a port called phi 1, and the ideal clock is named clock 1, and it has a period of 10 nanoseconds and a leading edge at 0 and a trailing edge at 5. So therefore the duty cycle is 50%. For the second example, the period is 20, the ideal clock is defined as clock 2, and it is set on pins named clock gen 1 /Z, clock gen 2 /Z, and clock gen 3 /Z, and these three are pins, and this clock has a period of 20 and duty cycle again of 50% because the waveform is defined as 0 and 10, so leading edge at 0 and trailing edge at 10. Now these three clocks, which are actually generated clocks, could have also been defined using the create generate clock command, but we actually are defining it using the create clock command, so which is just the same. The create generate clock can also be used for those cases if we want to relate them to a master clock. Now you can use the clock2 object to modify the clock signal on all the three pins, and basically if you need to change the period or you need to add uncertainty or things like that, it would actually be applied to all of these three clock pins. Try the following activity to improve your learning. Just like all other signals, clocks also have rise and fall times. The fan out of the clock is much greater than those of most other signals, so therefore the output slew degrades as the clock signal propagates through these cells. STA tools keep track of these maximum transition times on all the signals, including the clock. After creating the ideal clock, you need to refine it with specifics. So if you want to model the real nature of a clock, you need to add the transition times, uncertainty, and latency to the ideal clock. So in this example, we are specifying a slew of 0.38 nanoseconds on the rising edge of the ideal clock and a slew of 0.25 on the falling edge. So notice that getClocks is actually calling the clock object, and the clock object will actually indirectly call the related ports. Basically, we're defining things on the clock object. So any ports that are related to the clock 1 would all get the same slew and uncertainty and any other values that you set on it. You can specify clock uncertainty using the setClockUncertainty command, and the command actually has options for setup as well as hold. You can define separate uncertainties for setup and hold, or you can actually just set a clock uncertainty for both, which could also be done. So in this example here, we are setting different uncertainties for setup and hold. And so in the ideal mode, it would actually go by these values for setup and hold uncertainties. And in this case, the skew is actually kind of added in here, whereas in the propagated mode, you want to set uncertainty only to the jitter value rather than including both skew as well as the jitter. You can define both the source latency as well as the network latency using the setClockLatency command. When you specify a rise or fall, these would include the rise and fall transition times as well. But without those, you actually would just model the latency for when there is no transition time included. Now, as far as the source latency is concerned, you just specify the dash source option. But when you don't specify the dash source option, you're modeling the network latency by default. So in this example, the ideal clock versus the actual clock has different latencies. You can define different clock latencies for hold and setup using the dash early and dash late options. So the dash early relates to hold and dash late relates to setup. And so when you define clock latency dash source dash early, it implies that you're setting the latency for hold, and that is the source latency. This activity shows a timing report generated from RTL compiler, and this particular report shows the latency in the middle of the report, and what kind of latency it is, and basically what the following violation that is shown, what does it mean, and also do the activity at the bottom, which actually is asking a question as to why the early source latency plus early network latency is certain values and why is it not. So if we need to break it down, you can actually break it down and look at what the latency implies and try to understand the report and then answer the question. A generated clock is a fraction or a multiple of the source clock. And basically, as we discussed before, the purpose is to inherit the properties of the source clock. And because you can use it to model the outputs of multipliers and clock dividers, and the create generated clock command is what you would use to model such clocks. And it helps with defining the relationship between the clocks, especially when these clocks have data talking to each other or signals talking to each other. Then instead of having to unroll the clocks to find their base period, you already have an established relationship, and all the floating point calculations become easier. In the first command, basically the generated period is 1/3, and the one on the bottom shows that it's twice the period. So you can actually vary the duty cycles, you can provide different edges, and so on and so forth. And this actually helps in calculating the phase shift easily, and also to verify any data transfers that happen between these clocks. Generated clocks are helpful when you want to model a particular clock and inherit all the properties of the parent clock. So basically any uncertainties and things like that that you need to inherit, you can actually inherit from the master or parent clock. The other advantage of generated clocks is that when you have um, weird numbers or weird divisions that are happening, like 1/3 or something like that, the floating point you know numbers, the calculations are actually harder for certain tools to do, and therefore some kind of approximation is needed. But in the case of generated clock, you don't need to worry about such things, because you're just implying that it's 1/3 of a master clock or something like that, and so therefore it's easier to unroll the clocks. When you have multiple clocks in a design, you can actually verify any transfer of data between these two particular clock domains easily when those clocks are synchronous. But when they are asynchronous, it's possible that when asynchronous, we mean the clocks are actually generated from different clock sources, and therefore there is no clock period, the common base period, or there is no common LCM. And because there is no common base period, uh, the tools assume that the phase shift between the asynchronous clocks is 0, and also any data transfer that happened between asynchronous clocks is unreliable. So therefore you need to define false paths or functional false paths between these clocks, so that there is no data transfer that is happening between them, and it cannot be verified anyways. Some tools actually create synchronizers to actually synchronize asynchronous clocks. Now, that is outside the scope of this course. Gated clocks are actually quite common and can help reduce dynamic power dissipation, especially when you have a lot of flops in your design and you want to be able to control the switching of the flops. You can actually turn off the clock to those flops, and therefore save on dynamic power for your design. Now, in the case where you have gated clocks, uh, the data signal, which is the A signal A in this example, is the enable that actually enables or disables the clock that goes to clock 2. And clock 2 is the one that is driving the flops. Now, the signal enable A itself is somehow, an asynchronous signal that arrives at this point, or it can be a synchronous signal that arrives at this point. And for clock clipping, which is a side effect of clock gating, to not occur, this signal A must actually be a synchronous signal. And the synchronicity can actually be defined as either clock that drives A is the same as clock 1, which is the source or the root of clock 1, or it can also be that it is a multiple or an integer multiple of the clock root of clock 1. So in either way, in either case, any clock clipping would not occur. Now, what clock clipping is basically the data signal itself dominates the output of the clock gate, and basically your original clock is lost. In the case where your input A is at logic 1, then clock 1 basically propagates to the output clock 2, and it should be the same as clock 1. When A is 0, now the output is also 0. So therefore, the clock 2 itself is now a gated clock signal that is controlled by the enable signal A. When you run the setup and hold checks for this particular gated instance, the data must be stable. So the enable signal A must be stable, and it should actually pass the setup and hold checks for that gated clock. And so this particular gate must have these setup and hold checks defined in the library. And that's when you can actually use this clock gated element G1 in your design. You can also perform certain clock gating checks along with the setup and hold checks, and one of them is to ensure that clock clipping does not occur. So the clock clipping, as we've defined, is when the data signal dominates the output of the clock gate. So to ensure that that doesn't happen, you use the dominant value for clock input. So whenever you're using an AND gate or an AND gate, the dominant value is 0. And if you use an OR gate, the dominant value is 1. You can use the set clock gating check command to set checks for setup or hold on the pins of any design object that gate a clock signal. Now, in the example shown, we are setting up a clock gating check of 0.4 for setup and 0.2 for hold. So it'll look for all the clock gating elements and ensures that these checks pass. Now, the clock gating checks are inbuilt in some of the tools, the SDA tools, and they look for these setup and hold values in the libraries themselves and make sure that those checks are performed automatically. And so therefore, you might not need to set these clock gating checks. As we have discussed before, virtual clocks can be used to design combinational paths and make them meet a certain requirement. So if there is no actual clock source in your design to make that particular block or combinational path meet a certain requirement, you can actually use these virtual clocks. So in this example, if block B is to be synthesized and timed, then basically you can create a virtual clock and set the input and output delay relative to that particular virtual clock. Because these virtual clocks do not have a port association in your design, you can actually just use the create clock command without binding it to any port or pin. You can define the environment of a chip using the set input delay and set output delay commands. And you can, using these set input delay commands, set the arrival time on a port relative to a clock. So the set input delay, you specify delay value and you specify whether it's rise or fall, and you can say what clock it's relative to. So in this example, the input signal arrives at the in2 with respect to the clock 2 clock, and it arrives 4.3 nanoseconds after the active edge of clock 2. So that is how you're defining your input delay. For bidirectional ports, you can actually specify the path delays for both input and output modes. For multiple clock scenarios where a particular input has to go to multiple clocks, then you would actually provide that relationship using the dash add delay option. So if you want to specify that in relation to clock 1, this is the input delay, and in relation to clock 2, this is the input delay, you can actually specify the dash add delay option for each of the clocks. And that would give the multi-clock scenario that you need when that same input is actually going to different clocks in the design. Try the following activity to improve your learning. Ensure that you set the output delay using the set output delay command for all the output ports in your design, and this would actually ensure that all the register to output paths would actually meet the timing specified, and so therefore the tool actually uses this value to constrain the output ports. Let's look at how to set path exceptions using SDCs. Because the SDA tool creates exceptions to the normal timing calculations for all of the following items, they're called path exceptions. So multi-cycle paths are purposely additional cycles allowed for a certain path. False paths are something that you don't want the tool to actually time. So things like that. So we will look at each of these in more detail in the coming slides. By default, as you understand from the previous topics that we've discussed, STA tools assume that all timing paths are to meet timing in one clock cycle. Now, there are paths that require more than one clock cycles, and such paths are called multi-cycle paths. Now, in the case where you have a multiplier, for example, multipliers have to be pipelined, and in which case the pipelined output is then fed into something else. And so therefore, when certain exceptions are actually given to that particular path, because there is a data path component like a multiplier in that particular path, and it is a known long path, then the rest of the design is actually considerate of this known long path and only basically uses this long path only after certain cycles. Then basically it's a known multi-cycle path. And so therefore you don't want the tool to waste any resources. If it's a synthesis tool or if it's a place and route tool, we don't want the tool to waste timing resources and optimization resources trying to figure out the best way to optimize this particular path. And so in which case you make an exception. You tell the tool that this is a known long path and that it is a multi-cycle path and that it can actually skip optimizing it in one cycle. Instead, optimize it in so many cycles, and that's what you would actually tell the tool. And so in this example here, we are for setup saying that this particular path that is going through this multiplier is a multi-cycle path, and that it would require 2 cycles instead of 1, let's say, for example. So that is what you would actually tell the tool. Same thing for hold. You need to tell the tool that it is a hold multi-cycle path as well, and so therefore you need to allow for more than one clock cycle to verify the hold in this particular example. You can use the set multi-cycle path command to actually set multiple cycles for a particular path. So in the example shown, we are setting a setup multi-cycle path for the path from FF1B to FF2D, and in this case the setup 3 is what would actually do that. It would actually set all paths from FF1B to FF2D to 3 cycle paths. Now for the hold, it also automatically changes the hold check to 2 cycles or minus 2 cycles. So therefore, it would actually check the hold one cycle before the setup check. Now, if you don't want that to happen, and if it's supposed to be only a setup multicycle, then basically you need to let the tool know by setting another, dash hold as well. So in order to reset the hold for the multicycle path, you would actually then specify set multicycle path dash hold 2 for the same from and to, and then the hold would actually be done at time 0 back to the launch edge of the clock of the launch clock. So in effect, basically by setting the second multicycle path, you're canceling the effect of the first one for hold. For multiple clocks, you would use the dash start and dash end options along with the set multicycle command. Now by default, the setup checks are always relative to the end clock or the capture clock, and the hold checks are relative to the start clock. So in the case where there is no multicycle path constraint at all, the graphic or the waveform on the left, bottom left, is what you would actually see. Setup check is done at the first cycle after the launch clock, and the hold check would actually be done at the launch clock itself or the same edge. And so therefore, that is where you're actually seeing the checks actually done. Now, for the case where you do set up a multi-cycle path constraint, then and use the dash start, then basically using the start clock, it would actually go 2 cycles to the right and check the setup check at um, 4 or 5 cycles of clock 10, and so that is what actually it would do to actually move the setup check to after 3 clock cycles after the actual location where the check would actually have happened for the case of uh, no multi-cycle path. So, but if you use the dash end, basically it would use 2 cycles of the end clock, and so therefore it would have happened at the 3rd cycle for clock 10. Do the following activity to improve your learning. It is important to eliminate false paths so that the tool does not spend cycles trying to analyze these paths. Some Cadence software actually automatically flags these paths as false, removing the need for in-depth analysis of such paths by the logic designer. But you need to actually run those tools in order to identify those paths before you actually run static timing analysis on your design. For example, in this illustration, the path that goes from C to E to G to H to Z is actually the longest path. But after you do a bit of analysis, you can determine that C rising to Z falling and C falling to Z rising paths that have a delay of 5 units are basically false paths and can never be realized. And so therefore the path with the delay of 4 units becomes the real critical path. So in order to let the tool um, the SDA tool and the synthesis tool and the place and route tool know that the critical path that is identified immediately is not the real critical path, and that the one before or below that with the 4 units delay is the real critical path, is actually essential to avoid wasting the tool's time and resources, and just find better fit for it to work on other paths. Do the following activity to improve your learning. The set false path command can mark the uh, paths in your design that are specified using the start point and end point combination pairs as false paths. You can also use a specific through list to only set that particular path as a false path if you would like to. And so in the example shown, we're declaring that the path from U14Z to FF29 reset is actually a false path. And so basically the timing for that particular path is actually not done and is ignored, and the tools, basically including synthesis and SDA tools, will just ignore these particular paths from either optimization or timing essentially. Now, note that false paths do take precedence over multi-cycle paths. So essentially, you can actually try and avoid those kind of precedence issues by looking at your tools and seeing what their default settings are and how to avoid those pitfalls. You can also specify other settings like max delay or min delay, and those kind of settings typically override a false path command. And so those kind of precedence issues are something you need to watch out for. It is important to specify false paths very carefully because sometimes multiple paths might be affected. So FF1Q to FF2D has ton more paths than what you might want to set as false paths. So it might disable all the paths from FF1Q to FF2D when you probably just only wanted to set from FF1Q through U2 um, and so on and so forth. So make sure that your false paths are set carefully. If you don't want to use a specific timing arc of a particular cell because you either want to improve the timing or you just don't care to use that particular path through that particular cell, you actually can choose to use the set disable timing command instead of set false path. So basically the set disable timing command disables the timing arc so that neither the arrival times nor the constants propagate through it, whereas with the set false path command it only disables the arrival time information but constants are not affected. So any constants that you set might actually propagate through that particular path and or a timing arc. So In the case where there are combinational loops, you might want to break the combinational loops using the set disable timing command. In order to make a latch transparent, you can actually use the set disable timing command, and when you do that, the path from latch 1G in this example to latch 1QN is actually disabled, and so basically only the D to QN timing arc is transparent, and basically the tool propagates the value of D to QN regardless of the value of G. So uh, basically this would allow the latch to act as a buffer. So in the case where you want the tool to pretend as if a particular timing arc doesn't even exist in the library, uh, even though the library file itself does contain the timing arc, then using the set disable timing can achieve the effect that you're hoping for. Do the following activity to improve your learning. The set case analysis constraint is actually propagated throughout the netlist, and basically the timing tool behaves as if that particular constant is actually eradicating or deleting or optimizing that particular piece of the design, as if the tool itself has done it. Now, whether or not the actual constants are propagated through the netlist, to answer that, basically no, the netlist is not altered. It's basically only that the timing tool is pretending that the netlist has been altered. So any paths, so if we look at the example here, when you set the set case analysis to 0 on the test port signal, the timing tool will actually ignore all the paths for when the test port is 1. So all the crossed out logic doesn't exist according to the timing tool. A good use of the case analysis is to prevent large transition times on high fan-out synchronous nets. So the set false path command will not prevent transition times from propagating, whereas the set case analysis would. And so therefore it is a better use to set the case analysis on such nets. Do the following activity to improve your learning. Do the following activity to improve your learning. In ideal mode, you can actually use the set max delay that is set by this command to optimize the delays along a path and meet the requirements set by the max delay command. And the synthesis tools can actually benefit from this command being set. The min delay command can actually set a target minimum delay, and this can be helpful for the output ports in a combinational design, and or if you have to override the default single cycle timing for the paths where a multi-cycle path is actually not sufficient, then you can actually use the set min delay command. And both the min delay and max delays, they're basically used in synthesis when the timing or the clock is ideal. This example SDC file shows a few path exceptions in blue. The set case analysis command sets the TE1 port to 0. In other words, the paths are timed only when T1 is 0. The first set multicycle path command sets a hold multicycle of 1 on all paths from data to reg and the subblock. Now the second one actually sets up a multicycle path for setup of 2 and a hold of 1 on all paths from or through the mul net in the PCIM instance. Now the set false path command tells the SDA tool not to time the paths from GPC reg to GPX reg in the PCIM instance. So this is a sample example, and it's showing all sorts of different things, including create clock, create generate clock, set clock latency, set input delay, set output delay, so on.